So the topic of my presentation today is resolving inconsistency in building information using inserted knowledge graph, and I will use a case of building space management as an example to explain this. So this is a early stage research, and this is meant to be a proof of concept. So I'm presenting today on behalf of all my co-authors, Chang, Mohamad, Kassem, Ajith, Parlikad from Newcastle and Cambridge. So I think we can all agree that the construction industry is fragmented. So according to the UK data, a typical building project ranging from 20 to 25 million bucks, it can have around 70 subcontractors, and many of which is actually SMEs. This is because building nowadays is becoming more and more complex. So a single player or a single company does not likely to have all the skills they need to carry out all the work activities necessary for the building. For example, taking the building operation and maintenance as example, so we can see there are many contractors, like the general maintenance contractors responsible for repairing, daily cleaning and other small stuff, and also the contractors for HVAC, electrical, plumbing, elevator and lift, security, and other specific systems. And moreover, so the building owners team or their delegates are responsible for managing and running their core business as well. For instance, the space management is a core business for UK universities and other higher education institutions. So the fragmented nature of this industry results in the fact that the data collected and stored is also siloed, and they are owned and curated by different players. So for instance, for an organization to deliver its organizational goal, usually there will be different teams that will be responsible for a specific divided task or objective. For instance, in the buildings, we can see a lot of systems for different purposes. For instance, the computer-aided facility management system for general facility management purpose, computerized maintenance management system responsible for overseeing all the maintenance activities and resources, and the energy management systems for energy purpose, such like that. So each team would start collecting their data from scratch. So they are not using the data source from other, maybe some handover data, but they are not using the data collected from other teams. So that is a linear way. So the linear way is good in terms of that it is easy for this team to run their business. However, it is not necessarily the most efficient way. So nowadays, more and more research or industry practitioners start to look into the possibility of data sharing. So under the, whatever we call it, BIM, digital twin, common data environment, whatever it is, by solving the interoperability problem, we understand the data that other teams or other domains have. So this forms like this kind of improve the data sharing across the built environment sector. But the challenge I want to mention today is actually, we know that data start to degrade once it's being collected. So, for instance, things will change and a lot of things will happen. So, and different teams, they collect data at different time instance and with different interval. So it is very likely that if they collect some duplicated or overlapping information, there will be conflict. So there will be conflicting information that resides in the data storage or database that is run by different team. So an interesting thing is that, and also important thing is how we are going to deal with the conflicting information, and here we call it inconsistency that resides in different piece of databases. So to make it more clear, to make it easier to understand, I will use the space management as an example. So space management is about optimizing the use of space to accommodate the delivery of organizational objectives to maximize the use of space while minimizing the relevant operating cost. Why it is important for UK universities? Because the UK regulation says that the university must hand over statutory reporting to the HESA to reflect their space usage condition to get the funding for their teaching and research. And also, the other reason is that building another building might be even more expensive. So it is a better strategy and better practice to make best use of the existing spaces. So this is a piece of interview that conducted by my colleague Janet. So she has interviewed 7 university estate managers to find out what information they use during their daily operation, during their when they tries to generate the space utilization report. So this is a generalized diagram for the space management process. So as we can see, this process is still manual. It's still mostly a manual process, and it depends on the survey and inspection. But also, what the estate managers also mentioned is that there could be other resources, other data resources that contains the information that they can possibly use in their space management task. For instance, in the universities, different departments have employee record, they have space requirement for the employee classification, they have space availability. For the estate division, they have set site plan, they have room schedule. For the human resource, they have employee records, or in the finance system, they have employee payroll records. So these are potentially the useful information that can guide them, or that can give them a clear idea how the space is utilized in university, but it is not the current practice. So the goal of this piece of research is to find out, so if we could have other sources of information, what can we do, and what is the best technical strategy for that? So in terms of methodology, I'm not going to bother or going to torture you with all the mathematical and equations, especially because this is just after lunch. So, but I'm going to give you an overview process of how this whole process looks like. So first of all, the very important premise we have is that the building information can be transformed into RDF format in the triple form. So it means that we have subject, we have predicate, and we have object. So that is the typical RDF triple. So what we do is, under the Markov logic network, instead of treating each object as a point, what we have is that we have different ground atoms as the point. Ground atoms is actually representing both the subject, objective, and their connection. So it represents a connection, a relationship. So the next concept in the Markov logic network is the formula. The formula is this kind of atomic formulas that are recursively joined together or connected together. For instance, this is a logistic statement, which means that the two grounding, or the two facts, G1 and G2, they cannot happen simultaneously. So either one of them is true, or none of them is true. The last, and also, if we want to contain the uncertainty, we want to say that some people's piece of information residing in the database, they might be true, they could be true, or they're very likely to be true, or they're old and not updated. So it's not that certain, and this contains a lot of uncertainty. So we have the weight that indicate the credibility of this kind of formula. So for each formula, it indicates its credibility. So another important thing is that for a knowledge base or for a knowledge graph, the theory is that the knowledge graph can be represented by the conjunction of a lot of classes. So the class is actually the disjunction of the ground atoms. So, but anyway, so the interesting part is, the reason why we bring this is actually, you can see that we have different formulas. Different formulas are information either provided by the knowledge base as evidence, or it can be some common sense, something from the expert knowledge or something like that. It can be true, it can be wrong, but if it is from the expert knowledge, it is very likely to be true. So what we do is actually, we are describing the possibility of that kind of word. we have different parallel word. Different statement can be true, can be false, but we have this kind of specific word. We describe the probability of that word by using this kind of by using this kind of equation, which says that if one of the formula is true, then we give it a bonus. The bonus depends on the weight. The higher the weight, the more credit the formula is going to be true, then we give it a bigger bonus. Then the final objective is what we call the MAP, Maximum A-Posterior inference, which is we're trying to find a word that shows the biggest possibility, which means that is very likely to be the truth. So the important thing is that if there are inconsistency, so there is no way that all the formula we can get all the bonus because there is inconsistency. So the best thing is that we get the most likely case so if some statement or some facts, they're very old, they're not updated. So we are very likely to say that we could just not take it if there are other facts and evidence showing that the reality is something else. So what do we have? What this can do for resolving the inconsistency under the scenario? So we can see different databases as different systems. So as I said, the knowledge graph can be represented in a class form, which is the conjunction of different classes. The classes are disjunction of different ground atoms. So what we do is that we use the facts, or we call evidences, in this kind of knowledge graph or knowledge base, and then we add up with the expert knowledge or other constraints, and then we try to find the most likely word. So here's the case study. So this is a fiction scenario. So imagine that there are 4 staff working in the university, and there are one building of university shared by 2 departments, Department A and Department B, and there are 3 offices. So as you can see, staff A is affiliated to Department A, and it uses Office A, and it is very natural to say that the Department A has or owns Office A. The other case is that if staff B, we say that in the RDF graph, staff B is a member of Department B. However, and also he has the office, he used the Office B. However, we found that the Department A actually owns the Office B according to the space assignment plan. So what do we do? So here is the constraint we input. The first constraint means that if the member X is a member of Institute Y and he is based at Z, so we can believe that the space Y is actually owned by Z. And also, we assume that one staff cannot occupy 2 spaces, and one staff cannot be affiliated to 2 different institutes. So we transfer it in a class form with the weight indicating the certainty or uncertainty. So what we do is actually, so this actually is the result. So we can see that different this kind of constraints is actually connecting this 3 statement, and it actually gives the probability. If 3 statements are both true, then what is the bonus we could possibly get? So the final result is, so the hypothesis here is that the space assignment document is less believable, is less credible because it is long ago, but the employee record is more likely to be true because it is updated regularly. So we give 0.8 to the space assignment, and we give 1.6 to the other to the employment records, and we have the weights for this kind of statement. It turns out that as long as the weight is larger than 1.2, then we can solve the inconsistency by saying that Department B is actually owned by Office B, maybe because of later use. Okay, so final discussion and conclusion. So here we propose a very a method to resolve inconsistency using the Markov logic network, which is actually a combination of Markov network plus first order logic, and it can potentially solve the conflict within the collected information. And the important thing is that the information in inconsistent manner actually help us to link information from multiple sources without verification, because we know that they're consistent, and it helps us to gain efficiency when managing different information. the important things for the methodology is the design of weight. You can see that the weight is actually representing how credible the information or the fact is, and also the strengths of the constraints. So for instance, in the example that I give, if one staff can be a member of both two departments, then the weight of the third constraint becomes zero because that's not true. Okay? So the facts should be considered for the weight is, first of all, when the data is created. The newer the data is, the more likely it should be true. And whether it is automatically collected by IoT or by other things, if it would be more likely to be true, and also the trustworthiness of the constraint. If it is a expert knowledge, then it's probably true. If it's common sense, it's likely. And consistency is actually important for all the following data quality, like accuracy and timeliness. So the challenge to put it into using practice is that you transform the knowledge base and the corresponding constraints into first-order logic clause in an automatic way. Last but not least, it's the things that in addition to just sharing data, it is more important to coordinate, to collaborate between different teams in an organization, to collect how they collect data in a way that it would be more efficient to get most updated, most accurate data. So that's it. Thank you very much.